Good morning. This is Al Hoheb at the Aerospace Corporation. I'm the overall chair for the System Engineering Forum Virtual Series, and I've been the chair for our System Engineering Forum since 2016. It's my pleasure to welcome you to the talk today. With me is Alex Cheng, my co-chair for this year's events. He's going to be monitoring chat and helping our briefer handle those questions. Also in the background is our CorpCom production team, and I welcome them and their help across the series. So next slide, please. The System Engineering Forum is a set of virtual events that we kicked off this year. In the past, we had face-to-face events. The concentration is really on MBSE and digital engineering, as well as digital acquisition. And it's how is it applied across the space enterprise, contributing to mission success and fulfilling the vision of digital engineering and digital acquisition. These events have springboarded off our face-to-face meetings. We've gone virtual, as have most other forums, and we're planning to go virtual again in 2022. Our fiscal year starts in October, so you can look forward to some different talks starting in October of this year. These talks are applicable to a very wide range of participants, so they're listed below. The materials are cleared for public release, so you can reuse these. They're going to be posted in our System Engineering Forum archive. So if you look on the website and you click on the archive site, you'll see the reference materials for not only this talk, but previous talks as well. That includes videos, it includes the presentations, and includes background materials such as cleared papers and reports that are cleared for public release. The videos are also going to be available on the Aerospace YouTube video channel, so you can look forward to that and replay it from there. Next slide, please. Today's talk is In Depth with Dean Bucher, and we have two more talks this fiscal year. The outbriefing of designing for principles, which is how to look at system engineering with regard to principles instead of requirements. And then we're going to have an outbriefing on our model-based mission assurance and flight worthiness workshop, which is an invitation-only workshop. Next slide, please. We are recording this event, so your mics have been muted. And please keep your cameras off. That'll save bandwidth to make sure we can satisfy the demand. In the chat box, you'll see instructions if you need help on either reconnecting or how to use chat. But chat's pretty standard, so you can either chat to the whole group or to a very specific person, depending on your preferences. So think about that. We're going to handle questions as we go. So Alex Cheng, my co-chair, will be monitoring chat. He'll look at the chat questions. We have a couple of natural breaks in the presentation and the video. So during those natural breaks, we'll be able to aggregate the questions and handle those. We'll also handle it at the tail end. So we'll go just about an hour, and we'll have both a presentation and a video. The interesting thing about this talk is it's a video within a video. So we're going to post both the overall video and the in-depth video for your use. Next slide, please. Well, it's my great pleasure to introduce Dean Bucher. He's an associate principal director at the Aerospace Corporation and one of our key digital engineering transformation leaders. He has over 15 years of experience in enterprise systems engineering and architecting, performing portfolio and programmatic analysis, as well as strategic planning support to both the civil space and national security space. Mr. Bucher currently leads the Integrated Digital Engineering Prototype Testbed in-depth, the project we're talking about today. He's earned both a BS in mechanical engineering from the University of Missouri and an MS in aerospace engineering from the Georgia Institute of Technology. And he's working on his PhD in systems engineering from Colorado State University. So with that, Dean, I'm going to turn it over to you.
All right, thank you, Al. All right. Well, welcome everyone today. As Al said, we're going to be talking today about the Integrated Digital Engineering Prototyping Testbed Hub, which we'll be describing as our digital engineering testbed that we've been developing at Aerospace over the last few years, really to help support all of our various customers in understanding what the art of the possible is with digital engineering going forward. So when we set out to develop this digital engineering testbed, we had two key objectives for the in-depth project. The primary objective was really to demonstrate the value of an integrated digital engineering environment. And this is something that we're still working toward. Many of our government customers, as well as aerospace specifically, is working to stand up our own digital engineering ecosystems. But we really need to understand how to go about connecting all the tools, the data, and the analyses to really realize the vision of digital engineering in that integrated environment. The secondary objective, given that we have this, we call this a testbed, was really to use the in-depth environment as a means to provide plug-and-play experimentation for various tools, applying different standards at the both data level as well as modeling levels, and connecting data together in different ways using different standards, as well as applying different methodologies and approaches for how we go about bringing all of this together in a very real digital engineering way. The diagram in the bottom right is something that we developed early on to be able to really try to demonstrate or illustrate how we go about connecting this data together. Along the bottom, you see our key authoritative source of truth data sets that we've been working with: requirements, architecture, schedule, and finance, though we've extended on those to bring in a number of other ASOTs over the last year. And at the next level up is really where a lot of the key work happens to perform what we call enterprise integration. And this happens in two ways. At the enterprise data association level, this is applying different approaches to be able to really associate data across this complex enterprise of data authoritative sources of truth data types, as well as at the next level up, what we call enterprise data integration layer, is to be able to use that to be able to feed into various applications such as modeling and simulation, visualization, and decision support. On this slide, we show our really what we call our in-depth platform at a glance. And whenever I say platform, this is really intended to be just a collection of tools and models and data types that we bring together in a consistent way. At the heart of this is something we call our enterprise semantic data model, and there's an image of it over on the right in Cameo. And we define this enterprise semantic data model really to be able to define all of the data types that we might want to bring into the environment, and along with the relationships between those different data types at various levels of abstraction, from the enterprise level on down to the system and subsystem level for any given acquisition, or any other system that may not be an acquisition. We also bring together this and use various processes and best practices, leveraging authoritative source of truth. We leverage a cross ASOT data broker, something that is a COTS tool called Syndia. We've introduced the application of what we call semantic knowledge graphs or graph databases. And then we bring in, again, that application layer of visualizations and analyses using modeling and simulation applications. So when we set out this project, again, going on about 2.5 years ago now, we needed to pick an exemplar to really focus our efforts. And we selected the space-based environmental monitoring, or weather mission area, as our primary exemplar for a number of reasons. One, it was unclassified in nature, and so really allowed us to be able to have the flexibility of working in an unclassified domain. And we also wanted to bring together, use this because of the complexity of the space-based environmental monitoring mission area that spans multiple enterprises, specifically NASA, NOAA, and at the time, Air Force Space Command, now U.S. Space Force. We used a review that was that really kicked off back in the 2019 timeframe, a review that was called the Capability Area Strategy Review, led by Air Force Space Command for the space-based environmental monitoring mission area. And this was a periodic assessment of really what any given capability area, and we've held a number of them across different mission areas over the last couple of years. But this one in particular was really focused on the space-based environmental monitoring mission area and all the changes that were happening within that area, along with the need to address various gaps in the mission area. And so we use that as our exemplar and our focus going forward with the in-depth project, and set out initially to really do what we called a digital CASR. And you'll see that throughout the presentation here in various ways, where we still continue to use that premise of a digital review to be able to better understand and really understand the power of digital engineering in the context of not only conducting a digital review and the day of the review, but all the work that is needed to be done leading up to a complex enterprise level kind of review like that. So one thing I'll mention, and we won't be able to share this today, but we do have a much more technical and comprehensive video that's available, demonstration video that is 13 minutes long. It's something that we produced back in 2020, but it is unclassified FOUO, which is why we can't show it today in this form. But it is something that's under distribution B. It has been released by Aerospace and is available to any US government personnel. If you'd like to hear more about this video or gain access to the video, please feel free to reach out to me directly. My email is there at the bottom of the screen, dean.a.bucher@aero.org, and be happy to work with you to make this unclassified FOUO, now CUI, video available to you. So the key part of what we're going to talk about today with the InDEPTH project is our most recent Pathfinder, still using the space-based environmental monitoring mission area as our exemplar, but something that we wanted to extend upon that in support of the work that we're doing with US Space Force to establish US Space Force as a digital service. And we called this our digital US Space Force Pathfinder. This Pathfinder started by really creating what we called a vignette. And we wanted to create a complex vignette that set out to bring together all types of different kinds of analyses, data sets, and really span the spectrum of not only digital acquisition, but other digital types of functions that are needed to be able to support US Space Force as a digital service. And so I'm going to just very quickly walk through the vignette to give you an idea of the complexity of the work that we did here. But we started with the programs of record for not the entire space-based environmental monitoring mission area, but really just a subset that's focused on the cloud characterization and theater weather imagery mission areas within that overall weather mission. So we start with 5 GEO and 3 LEO polar constellations as the programs of record. And as we start to walk from left to right here, we explored what the impact would be to a change to warfighter needs. And specifically, we addressed a change associated with the revisit time needed to support the warfighter. We also look at a enterprise capability assessment. And so this is looking at not only what the impact to different changes within the mission area itself, but those other impacts associated with gaps that might be tied to related mission areas or supporting enterprise capabilities like space domain awareness, command and control, and what we generically called protect and defend. We also explore the need to introduce the threat as a key premise for US Space Force and the need to outpace the threat. And so we bring in an IC threat assessment, IC being the intelligence community, bringing in a threat assessment to assess vulnerabilities against that baseline, and then bring in the notion of a terrestrial weather mission thread. And so this is a modeling approach to bring in and model specifically the mission thread in the joint fight. So typically, in this case, we used a unmanned aerial surveillance mission thread to be able to understand the dependencies on the weather mission area. As we continue to move across, we see changes happening in the context of the vignette where some of the constellations are deemed inadequate. Specifically, the LEO constellation is deemed inadequate to meet requirements, as well as the GEO assets that cover the Indo-PACOM theater is deemed inadequate to meet the enterprise requirements for survivability. And we also introduced the notion of performing an enterprise requirements analysis to better understand those survivability and interoperability requirements across the enterprise. As we continue to move across and we better understand the problem space, we now move into the solution space aspects of the vignette where we perform a concept development trade study and generate new concepts for both a proliferated LEO option that will be, or options that would be looked at to better understand and meet the revisit time requirements for now this new set of requirements, as well as we look at a GEO solution tied to the Space Combat Bus, which is an enterprise family of buses, family of systems that is being explored to better equip ourselves going forward across not only this mission area, but multiple mission areas that may use that Space Combat Bus going forward. As we continue to move across, we then get into the aspects of needing to go into a digital POM planning mode, or the PPBE process, and support that, as well as an enterprise needs analysis to understand what those dependencies are and the additional investments that may be necessary to make any solution successful at an enterprise level. And then we move into a enterprise decision forum that really tees up these decisions in a digital way to support digital reviews within a common framework, and explore how we go about generating government reference models and using MBSE techniques, but also auto-generating these from those concept design trade studies. And lastly, we talk about an operations digital twin and establishing the platform that would make use of those digital twins early on in the life cycle for any given development. So moving on to the next chart, this is the overall data and software architecture we used with InDEPTH, specifically for this digital US Space Force Pathfinder. And without going into too much detail, I'll just orient you to the various layers that this utilizes. So at the bottom, we have a descriptive data ASOT layer that pulls in all those descriptive data ASOTs. I apologize, I'm getting a error message on Teams. Hopefully this works. The descriptive data ASOT layer at the bottom is where we'd really define all those ASOTs associated with requirements, architecture, schedule, as well as a number of other areas that really need to be pursued in order to describe all of the authoritative data needed to feed into the rest of the Pathfinder. Along the right side, we have two other ASOT types of layers. We have what we call our analytical ASOT layer, and this is where we define the technical attributes needed to feed into and technical parameters needed to feed into a number of modeling and simulation capabilities, things like sensor parameters, orbital parameters, and on down to a number of other really detailed sets of information that's needed to feed into higher fidelity modeling and simulation. We also have what we call our engagement and wargaming models that are needed to define those types of behavioral aspects associated with any given engagement scenario between red and blue. And then we also have our database that really is the repository associated with all the technical data needed or that comes out of these conceptual trade studies specific to our Aerospace Concept Design Center. In the middle layer, we have our enterprise integration layer, and this is really, we use two different approaches here to be able to integrate and associate the data across all of these different ASOTs. We utilize a Syndia, a COTS tool called Syndia, combined with Cameo Systems Modeler to bring all that data together using that enterprise semantic data model that was mentioned earlier, and generate an enterprise integration model in Cameo that can be then exported into a couple of different ways, a relational database in MySQL or a graph database in Neo4j. We also use the in-house tool called the Huddle Web Service. This Huddle service is a project that's been going on for roughly 5 years now within Aerospace, and uses a common ontology, defined ontology, along with semantic data mapping approaches to be able to serve as a data translation and transformation service to bring all of these authoritative sources of truth into that service, and then translate it into various modeling and simulation applications. And then at the last layer here is our visualization and modeling and simulation layer that's comprised of various modeling and simulation tools, varying from performance analyses to resilience analyses, as well as various wargaming tools and decision support tools. And with that, we'll move into the digital US Space Force Pathfinder video. This video that we'll be sharing is 7 minutes long. It is really intended to be an executive level illustration of the art of the possible for establishing US Space Force as a digital service. It is approved for public release, and so we will be, again, as Al said, making this available to everyone and posting it to our YouTube site at some point in the near future. So with that, I will stop sharing and reshare the video. The video itself has its own voiceover, so I will be going on to muting my own video and or my own audio and sharing the video.
Digital United States Space Force. In the modern space arena, our adversaries have elevated information superiority and decision speed to be central components of their doctrine. To ensure that the U.S. Space Force can outpace the emerging spectrum of threats to the space domain, it must be able to analyze information and take action far more swiftly and decisively across all aspects of leadership, acquisition, engineering, intelligence, and operations. To enable the speed and agility required for today's threat environment, the Space Force will develop and fully embrace digital engineering technologies and methodologies in order to rapidly mature innovative concepts into integrated solutions and deliver critical warfighting capability at the speed of need. By cultivating a digitally fluid workforce functioning within a highly integrated digital engineering environment, the Space Force will establish the interconnected foundation necessary for effective collaboration across the digital service. To demonstrate the value of a DE environment, Aerospace developed the Integrated Digital Engineering Prototyping Testbed Hub, or InDEPTH, as a precursor to the U.S. Space Force's effort to establish a digital service. This DE testbed enables the prototyping of DE applications, methodologies, and processes in a controlled environment to better understand the appropriate application of methods and tools for the digital integration of a complex enterprise. The testbed architecture consists of different layers, each of which is composed of multiple datasets, software applications, and tools. The layers include authoritative sources of truth, or ASOTs, for descriptive data, analytical data ASOTs, enterprise integration, alternative concepts, modeling and simulation, visualization and decision support, and data science. Using the Space-Based Environmental Monitoring Mission Area as an exemplar, Aerospace created a digital thread to demonstrate the art of the possible for how portions of the U.S. Space Force might operate as a digital service. In this notional vignette, the operational need for timely, high-resolution weather intelligence has evolved to require an increase in revisit frequency to improve refresh timelines of terrestrial weather data over the Indian and Western Pacific Oceans, while also improving the resilience of GEO satellites providing persistent coverage over those same theaters of interest. To demonstrate this change in mission requirements, various tools, processes, and analyses are integrated into the vignette through multiple digital workflows executing in parallel. In prior exemplars, the in-depth testbed demonstrated how multiple ASOTs can be updated and independently committed by ASOT owners to the DE environment to establish a single integrated source for trusted blue architecture data. The enterprise integration layer defines all the data associations between each ASOT across different levels of abstraction using a common standards-based enterprise semantic data model and applies a common ontology to provide on-demand egest and ingest of authoritative data. By combining this integrated blue architecture database with a digital red threat database, interfaces and interdependencies are defined and exploited to support digital threat assessments. Analysts can quickly and efficiently identify and evaluate blue vulnerabilities and execute resiliency analyses based on authoritative data defining the interfaces and attack vectors between red and blue assets and capabilities. In addition, joint mission threads are modeled to dynamically bring red and blue architectures into contact with one another to evaluate the relative impact of various threats on mission execution and the probability of mission success. To ensure the long-term survivability of the mission, InDEPTH leverages connectivity between requirements management and architecture modeling toolsets to illustrate a cross-mission survivability requirements analysis for enterprise solutions, such as the Space Combat Bus. Informed by digital threat assessments, this model-based analysis enables enterprise requirements to be derived based on cross-mission needs to inform the acquisition trade space between mission performance requirements, enterprise survivability requirements, and system and architecture design constraints. Using concurrent engineering methodologies for a concept design trade study, alternatives for the Space Combat Bus and proliferated LEO conceptual designs can be assessed against the cross-mission survivability requirements trade space. Once a concept or family of concepts is identified, the resulting solution parameters can be utilized in an enterprise needs analysis to evaluate any additional dependencies required to integrate the concept into the enterprise. In order to better understand how the conceptual design will integrate into the mission architecture and to streamline the pre-acquisition process, a model-based systems engineering reference model utilizes data from an alternative concepts database to auto-generate a populated MBSE model, including multiple artifacts required to support the defense acquisition process. These auto-generated models authoritatively define relationships between requirements, systems, and capabilities, and serve as the point of departure for a government reference design, or digital twin, that will be matured and accessible through the life cycle of the program. To enable the facilitation and execution of critical reviews, a web-based enterprise decision forum provides an interactive venue that gives users and stakeholders a centralized environment to collaborate and provide real-time access to process instructions, requirements, ASOT data and models, analysis, and more. This virtual forum allows for a state-of-the-art means to streamline review processes, from design reviews to budget formulation reviews, and enables data-driven architecture and acquisition decision-making across the space enterprise. Lastly, modeling and simulation tools are integrated with the digital twin platform and used to verify mission designs and planning success. These simulations incorporate previously defined physical and behavioral models that ingest real or simulated inputs from established conceptual and ASOT data sources. Leveraging visualization tools to simulate data-driven interactions between red and blue engagement scenarios, operational courses of action can be evaluated to support U.S. Space Force wargaming and force design analysis. Leveraging the digital engineering tools, processes, models, and data, and alternative concepts developed through the InDEPTH project, Aerospace executed a digital thread to demonstrate how the U.S. Space Force might operate as a digital service. While the full scope of a digital service is far greater than the applications demonstrated by the InDEPTH digital engineering testbed, this video serves as a glimpse of the art of the possible for a truly digital United States Space Force.
All right, and as I transition back to the slides, Alex, are there any questions that you'd like to take at this time?
No, Dean, you're good. You're good to go.
All right. All right, so moving forward in the presentation. So the next, based on the video, what we wanted to do next is really break it out into the various kind of key demonstrations that we've completed with the digital U.S. Space Force Pathfinder. And we have six different breakouts here that we'll talk about in a little more detail than what you saw in the video. The first is the digital enterprise capability and threat assessment that's combining a number of databases along with a weather mission thread. The next after that is a digital enterprise and cross-mission requirements analysis. This is specific to the Space Combat Bus, as you saw in the video, and the notion and work that's being done to establish enterprise survivability requirements. Next is a digital POM planning proof of concept, where we utilize an aerospace tool called PDST, Portfolio Decision Support Tool, to lay out an approach of how the POM process might be conducted in a more digital and data-driven way. A digital enterprise decision form using the Confluence web-based capability to support this type of forum to conduct any type of digital online review. And then a concept development, our concept design center generated, CDC generated government reference model. This is using really a number of capabilities that were highlighted in the video, but bringing them together to be able to auto-generate an MBSE model that can be used to serve as a point of departure for a government reference model. And then lastly, we'll talk a little bit about our Digit Engine Sim Engine capability that we've been developing to serve as a digital twin platform to be able to bring in not only digital twins, but other associated authoritative sources of truth to be able to support various wargaming kind of scenarios. So starting with the digital enterprise capability and threat assessment, you'll see this chart again and again where we highlight specifically what we call out as the primary nodes that are bringing all of these things together in a combined demonstration, as well as the interfacing nodes, those things that may either serve as key inputs or key, in this case, key outputs that the digital enterprise capability and threat assessment supports. So moving on to the next slide, this is where we'll talk about specifically a couple of databases that are being developed and supporting both U.S. Space Force as well as Space and Missile Systems Center to bring together and define authoritatively not only blue architecture, but also the red digital threats. And so one is called the GRACE database. This is being developed again in support of SMC and U.S. Space Force, but combines really in a graph database, combines a number of models that span everything from MBSE models to various databases, as well as our aerospace portfolio decision support tool model that spans really a lot of the national security space assets that exist. And so we bring all those together and leverage those databases and use this piece of the demonstration, again, scoped to the terrestrial weather mission area, to be able to define an approach for defining interface nodes between red and blue assets, as you saw in the video. Based on, by doing that and defining those different interface nodes, we can support various vulnerability and resiliency analyses. We then combine that with defining a joint mission thread, as mentioned earlier, a unmanned aerial surveillance joint mission thread that utilizes the cloud characterization capabilities, both in LEO and GEO, and taking that mission thread and linking every step of the mission thread to various parts of the red and blue assets that are supporting them. We can then execute that mission thread in a Markov chain analysis to evaluate the probability of mission failure and mission success, as well as be able to understand the relative impact of different threads resulting in mission failure. And so this is really a first order high level type of modeling and simulation analysis that we created to be able to support this particular part of the vignette. But it represents how both blue and red ASOT data can be combined with joint mission threads to be able to support a number of various analyses in higher fidelity tools such as AppSim and any other types of resiliency analyses you might want to conduct. The next part of the demonstration was a digital enterprise and cross-mission requirements analysis. This work leveraged some of the work that is being done in support of Space Combat Bus to look at how we go about defining enterprise requirements for survivability in a cross-mission way. So looking across various missions specific to not only the weather mission area, but things like SATCOM, TNT, ISR, OPIR, all of these various missions that space provides support to, being able to look across those and look at the survivability requirements across those various mission areas to be able to understand what are the, how do we bound the problem space associated with those requirements. And then we focused in on, because we wanted to keep this an unclassified demonstration, we focused in on the natural survivability requirements for natural space environment, as well as those for nuclear hardening and things such as that. But we wanted to be able to bring in those types of requirements and understand by leveraging not only requirements management tools such as DOORS NextGen and JAMA, but also architecture modeling tools such as Cameo Systems Modeler, bring all of that together in a common way to be able to understand really what is the trade space associated with the requirements themselves, as well as how does the threat drive certain requirements, and how do we use that requirements trade space to better understand the solution space associated with design parameters for a concept design trade study. The next part of the vignette was a digital POM planning proof of concept. And so utilizing, again, our portfolio decision support tool that we have at Aerospace, we defined a set of criteria, structured criteria, that really helps us to understand and evaluate the investment portfolio trade space in a systematic way, as well as be able to understand, using those criteria, how certain data and analyses from these various authoritative sources of truth, as well as the related associated analyses that were conducted within InDEPTH, how those would feed into the evaluation of those criteria, looking across various POM or PPBE portfolio options. Specific to the Digital U.S. Space Force Pathfinder, we looked at next generation, multiple options for next generation of the SBEM architectures. Again, these were driven by the concept design trait study, but being able to understand the various pros and cons and strengths and weaknesses associated with each option, we went through the exercise of evaluating every one of the criteria, which you can see a snapshot to the right of a pretty comprehensive set of criteria that were defined. And we did this in a combination of leveraging, again, the authoritative source of truth, the analyses that were conducted, as well as SME evaluation. Next is the Digital Enterprise Decision Forum. And as you can see, this is really the culmination of leveraging all of the work that had been conducted previously and bringing that all into a common forum to be able to support decisions at that enterprise level. And so specifically, we used Confluence as a means to just be able to bring this together and demonstrate a proof of concept of what an online forum would be for combining all of these authoritative sources of truth, as well as all the analyses in one place, but then really laying out and defining the process associated with various user teams, as well as stakeholders, on how they would go about interacting within this common forum, to be able to not only facilitate the day of review, but all the work that needs to be done to lead up to a review in a common and standardized way. We had two different use cases associated with this enterprise decision forum. As mentioned previously, we leveraged the architecture review approach for the capability area strategy review to support a no-go decision associated with that, and use that as one of our use cases, as well as an acquisition process review for an enterprise systems requirements review. And this is something that we're continuing to evolve for various customers to support these types of reviews in a very real way going forward. Next is the CDC generated government reference MBSE model. And so again, using the underlying databases associated with our concept design center that we have at Aerospace, we leverage that underlying database and all the wealth of data that comes from any trade study that it supports to be able to auto-generate an MBSE government reference model. And really this is intended to serve as the point of departure for a full government reference model that would be used for supporting RFPs, as well as the entire acquisition process for any new acquisition. But we use this by leveraging the various tools associated with the CDC, as well as the huddle capability that we mentioned previously. We were able to take the data from the CDC database, translate it into a Sparks common reference model. So this was a reference model that has all the defined pieces that you would want to see in a reference model. And then we created the code to be able to auto-generate various, not only the translation of the data into that common reference model, but also the various artifacts that are needed to support the acquisition process. And so specifically created a number of different package diagrams associated with the model content, different block definition diagrams, and IBDs and BDDs associated with system requirements and various capabilities, as well as parametric diagrams associated with the analyses that were conducted within the InDEPTH platform, specifically those tied to our Space Enterprise Calculator performance analysis capability. And lastly, we have the DigitEngine SimEngine digital twin platform. This one is specifically taking, and we use digital twin very carefully here, but the intent is really to provide a platform that we can take digital twins that are being generated by industry and at the system level, to be able to bring those in a common way into a platform that can combine it with other authoritative sources of truth, such as those for our digital threat model database, as well as the GRACE database for the Blue architecture data, bring in those digital twins associated with that, and then combine it with behavior models that are created to be able to define the engagements between red and blue assets, these can be done at a 1v1 type of engagement level, as well as a many-on-many kind of engagement level. There's multiple efforts going on across the community to define these behavior models using activity diagrams, finite state machine diagrams, but do that in a way that we can then combine that with underlying physical models that would be coming from digital twins, and bring all that together into what we call our sim engine capability that really plays out the engagement scenario along with all the underlying physics needed to support those engagement scenarios, and bring that all together in our digit engine visualization capability so that we can evaluate and visualize the engagement itself, as well as understand the outcome, parametrically the outcome associated with various engagement scenarios, and then start going from there, where we can really evaluate different COAs tied to any given engagement, understand changes to designs and various design traits that might impact the outcome of any given scenario, but doing that all in a common platform. And with that, that is the end of the presentation. And so happy to go back and revisit any part of this, or take any questions tied to the video, tied to the overall InDEPTH project, or any part of the digital US Space Force Pathfinder that we provided today. Alex, do we have any questions in the chat box?
We do not have any questions in the chat box at this moment. If anyone would like to, oh, we do have one from John Day of JPL. On the digital twin slide, how are the different elements interfaced?
All right, going back to that slide. So they're interfaced in a couple of different ways. One is within the sim engine capability, which we can provide more detail on that if you're interested in hearing about it, but without blowing up the box there. But the sim engine capability specifically brings all that in kind of a common way. We have, and you can see it's separated into, we have it separated into low resolution, mid resolution, and high resolution capabilities. We're using that sim engine capability actually to support a number of other wargaming kind of capabilities that we're developing at Aerospace as well. But what it does, it really, it has a queuing mechanism, as you can see in the diagram, but it is able to manage not only the data coming in from those, but actually the execution of some of those, because some of these models are executable models in of themselves. So it's executing and tying together the inputs and outputs associated with each of the underlying models and underlying simulations, and doing it in a coordinated way based on what is actually going on and being defined within that the behavior diagrams and the sequence of events that are happening within any given engagement scenario. And again, we can provide more detail on that if you're interested. Feel free to reach out to me and be happy to connect you with that team to provide more detail and some more examples of how we're using that. All right, any other questions, Alex?
Looks like we've answered the few questions that we had. And Dean, I want to thank you so much for an outstanding presentation. And I really want to add kudos to the whole InDEPTH development team. They've done a tremendous job in providing this capability. So let's go to the next slide. I have 2 slides to close. So the proceedings are available a couple different ways. We have the presentation slides available at the System Engineering Forum website, so you'll be able to download those. We'll have recordings of this session, as well as the InDEPTH standalone video available for download, both on the System Engineering Forum site and also on a YouTube Aerospace channel video link, so you'll be able to see that. We're going to follow this up with our survey. It's a quick 5-question survey. How did we do? An important aspect for me is, what other types of presentations in digital acquisition, digital engineering would you like to see? And that will help us formulate our way forward. Of course, you can register for any of the follow-on events, and look forward to our email sometime in September, which will notify you of our slate of 2022 offerings. So last slide, please. This concludes the formal presentation, and we can stop the recording and then start the archive. Thank you for your participation and your interest.